Good morning to all the machinists and welcome back to our channel. Today, I would say good news. Let's make a nice video with an example of working with Sinutrain, featuring our great ShopTurn and some new updates. I had told you that it's a shame that with ShopTurn you can't specify the dimensions of a raw casting. I told you something wrong. Huge news, fantastic. ShopTurn. The more I use it, the more bad word I fall in love with it. With ShopTurn, we can define a casting, and that's really interesting. It really saves us time. So much time in programming, of course. When defining a casting, always stick to the maximum tolerance. Keep in mind that you will probably be clamping onto a raw piece, so the part might not be perfectly concentric. So, either you keep yourself in a safe position when you get close, or you always define it a bit chunkier than it actually is. But in our case, this isn't a problem, because we are lucky simulators, so we won't crash. At worst, we might generate some programming errors. Once you're on board the machine, things change. So, I recommend that when you're at the machine, always keep yourself on the right side of things. On the right, you can see our part, the drive shaft as we call it. It's always part of the standard examples you can find in the books. Using Sinutrain, doing it with someone to guide you can be helpful for those who are less experienced. And this is where I come into play. So, as always, Program Manager, let's go to the Parts folder and tell it New. New. We always open a new folder as usual. So when we click OK, we don't create the program, but rather the folder, it automatically gives us the name Program Shaft of Diversion, right? And it tells us the last time worked in ShopTurn. So let's continue like this. Otherwise, we could work in G code. And by now you should have learned this. Perfect. The first thing it asks me is about the raw material. And here it's all old school. We have a piece with a maximum diameter of 90 millimeters. Let's keep working in this direction. So, maybe we have a raw piece. I prefer the graphical view. A raw piece that is 100 millimeter long. So, minus 100 with a projection from the clamps of 91 mi. 100 and minus 91. There we go. We can leave everything else as it was in the last entry, except. And here you might say to me, but you just said that I can define a raw piece, and now you're not defining it for me. Don't worry. So, as the first thing, let's go to turning. So, turning, roughing. Let's select. We already have it. A roughing tool. 0.25 per revolution. 240 meters. Perfect. X0. We set it to 60. Attention! Regarding our raw material, so here we have an M48. We consider that our actual raw material, so not the one we programmed, has an outer diameter of 60 millimeters. Okay? Has an outer diameter of 60. Okay? Okay. X 1.6. Xeon. Zero. So, roughing. Here's what I was missing. I was missing this part of the program. What do we tell him? With a maximum increment of 1.5. But it won't do anything to us. And then we give it an excess material in X of 0 and in Z. By 2/10. We accept this. For those who haven't followed along, the reason I didn't have these 3 boxes is that I had entered the finishing and not the roughing. Okay? Let's accept and simulate what happens. What happens is simply this. Look. Okay. Let's chamfer our piece. It's a safety chamfer in relation to our piece. Raw. Okay? The raw piece that we currently see simply as a cylinder. Okay? Turning profile. And now comes the fun part. New profile. And we will call it raw. Accept. Now, let's define our profile. First of all, the starting point. In this case, it must be strictly x0. 0. Okay? Let's accept and define our profile. Okay? All right. Having entered the first point, we need to insert the profile of the raw piece. Here we see it outlined, but here we see it quoted. So, neither more nor less, as I taught you to insert the profile of a finished piece. Let's insert the profile of the raw piece. Okay? All right. Let's follow the drawing of the figure highlighted in red. So we go up to x60, accept. And here we are. Now we go to the left at z minus 40. We accept, and here we are. Now we go diagonally. X 80, z minus 45. We accept. Then to the left at z minus 65. And here we are, going diagonally to x. Z minus. We accept and finish at z minus 100. You see that we've made a nice shape. Here it is down here. You see a soft case, which takes me out of this menu to close the tack profile. Here is the upper section of our blank. We accept it and we have inserted the blank. All right, let's go ahead and insert the turning profile. It won't be easy, and let's try not to make too many mistakes live. But if I do, well, I will comment with you and we will come back, step by step. Turning, profile, new profile, name. Profile, we accept. Let's start from the center of the piece, which is fine for teaching purposes, and let's begin to move, as we already know. We're going up to x48 and finishing with a 3 mm chamfer. As indicated in the drawing, it makes the line, but it doesn't create the chamfer. Now we need to move horizontally to the left, but we haven't defined the arrival z. We only know that we need to finish with a radius. As shown in the drawing, he makes the line, but does not make the chamfer. Now we need to move horizontally to the left, but we haven't defined the arrival z. We only know that we need to finish with a radius. And here Siemens can help us, but it won't make things easy for us. We accept it. You see, it draws a line for me. Okay. A segment, a line without an end. Without direction, it's dashed because it tells me there's something wrong, something doesn't add up. Perfect. At this point, we need to do a circular interpolation. Here it is. The tool's direction of travel is clockwise. The radius of our interpolation is 23. The final x is known. It's 60. Perfect. At this point, we need to do a circular interpolation. Here it is. The tool's direction of travel is clockwise. The radius of our interpolation is 23. And we know the final x, which is 60. The final z is not something we know. However, we have the option to insert the circle center relative to the x-coordinates. Look, if I set it to super, it tells me circle center. The center of the circle is 34.217, the distance from here to here. Plus 23, 40 mm, We always enter a diameter measurement because we are turners, and we say 80. Let's move to K. And you see that tucket is already telling me, look, I can make two circles. With these coordinates, one to the right of 0 and one to the left of 0. I select dialog. You see, it highlights one or the other in red. We already know that we are to the left of 0, and I accept the dialog. But as you can clearly see that it selects a circle, let's say with dimensions that aren't correct, but I still have it active. Select dialog, you see I press it and it says, look, I can even stop right there. Okay, so accept the dialog. Okay, and here comes the difficult part. After selecting the construction method to create the arch, which is a crucial step in the process of creating the arch, you need to carefully enter the value K35, which is specifically the position of the tolerance center relative to the 0 point on the scale, and must be done with precision to ensure accuracy. But if I go to K35, it doesn't allow me. So I accept, and it doesn't let me. Radius 4. Perfect. Here's what the problem was. I don't know if you noticed the case was in incremental, but I need to switch, you see, from incremental to absolute, and I have to give it minus 35. Accept. These are small nuances that can make you lose an hour. As you can see, I can guarantee that too. I had prepared this because I knew I had forgotten again. Okay. Me. At this point, I would delete the element and repeat the operation. Okay, we're back. We've gone back to where we only had an indefinite line. Horizontal, that is, the crest of the thread. Let's insert our circular interpolation. We give it the direction of rotation, the radius of the interpolation that we are going to create, all the coordinates that we have available. In this case, the x, which is 60, is the end radius position. We don't have the z. We have the center of the radius at or centimeter. At this point, the smart machine tells us I can create two circles. Which one do you want? With the dialog selection, I select in red the left part. I accept the dialog. There's something that doesn't add up. I'm going to see if the machine can communicate with me, and by selecting dialog, I'm going to insert this part and accept dialog. What should I do? I need to enter the center coordinate in incremental mode. Something doesn't add up. I transform it to absolute, and I'm going to enter this z minus 35. Then I'll enter the radius 4 chamfer. Radius 4. It was tough, but we made it. Okay? At this point, I'm moving to z minus 75 with a horizontal linear movement, z minus 75. I finish with a radius 6, I accept, and I'm going to enter this point using an inclined movement. And the coordinates I have available. So, x90, z minus 80, radius 4. We accept. And we're going to finish with a z minus 90, and then we accept. And we accept again. We have defined the perfect profile. It's time to start thinking about our machining. So, we're still going with turning profile. And let's start talking about roughing. Roughing that will require a tool that allows me to create an undercut. In this case, we're going to select a tool. So, Rudin, CNMG. So this is an 80 degrees. Let's proceed to our detailed tool inventory list, where we can carefully review and gather all the essential equipment and tools needed for our upcoming tasks. Let's ensure everything is organized and ready. Here, you can see that it has already been modified because I used it in a previous program. So let's go ahead and change the label. The NMG tool is often used at a height of 15 metro. So 150608 for roughing that isn't too thick. Let's transfer it to the program, telling our machine that it can operate at 13,000 RPM. At the turn, we need to do a nice roughing, then finishing. So we use the same tool for finishing. We'll go a bit slower on the feed rate. I wouldn't push a DNMG beyond 3 mm of cutting depth. And we'll do the undercuts. Now, profile. Let's see if everything is in order. Millimeter turn undercut. Here, be careful if you leave a cylinder here. It will work as a cylinder. If you press excess material, it will only rough the excess material. In this case, we definitely need to specify the profile. Profile isn't a standard name. It's the name of the subprogram I chose when I created the profile. In this case, we must necessarily indicate profile. Profile isn't a standard name. It's the name of the subprogram I chose when I created the profile. Be careful, because often you'll be working under these conditions. As a result, you need to change this wording. Let's accept and simulate. Okay, what happened? Now I'll explain it to you. When we have shamed the piece we have used, and this is a mistake, I used a tool that I then went and modified. So now this tool is no longer found. For convenience, I'm going to select the same tool. Do you see? We accept. Actually, you should have set up a turret with a CNMG tool for facing and a tool for roughing if you wanted to. Here we go. You see that the problem was all right there. I hope it's clear. So now in 2D, can you see what it's doing? It completely ignores the cylinder and goes to make the rapid approaches. Where necessary, see. Here the mistakes. Here they are, the mistakes that can be made for carelessness. But it is also nice to make mistakes, because with the mistakes you understand, and next time you improve. So, let's take a step back, and then we'll revisit the discussion. So let's do a thorough and complete job. We're going to rough where we're going to face in the process, and ensure that we are fully prepared for the challenges ahead. Select the tool. Let's carefully go to the tool list and create something more appropriate. A tool, so we load. Interruption, selection, storage, new tool, such as a roughing tool, and also, for example, a roughing tool. And we give it OK. Here it is. Let's empty position number 1, unload it, and take the roughing tool to load it into position 1. It will always load it into the first available position. Then we go to get the DNMG and load it. You see, it loads it into position 18 for me, and if I want to load it somewhere else, there's no problem. Now roughing, let's transfer it to the program, accept, then I load it somewhere else. Now, roughing, let's transfer it to the program, accept, then. Here we have a rough cut that I have divided. I did roughing and finishing at the same time. It's not working for me anymore. So I just do the roughing and select the correct tool that I put in position. et photon. Okay, then I accept, go back to turning profile, roughing, finishing, and I'm going to select the tool at 35 degrees. This will be able to execute this profile. Roughing, finishing, and I'm going to select the tool at 35 degrees. This will be able to execute this profile. Perfect. Feed rate, we set it to 0.2 per revolution and tell it that it can execute the undercuts. We accept and simulate. Now, let's do it quickly first. Look at the roughing. Do you see where it's going to work? It goes where the rough exists. Touch it, rough it. Obviously it can't go down here, but the finisher will come in and be able to do it. Now I check the program, and there. Single block back. And let's start from the top. Perfect. What does he do? He creates a cylinder, sees the raw material I gave him, and starts. Here, pay attention. We don't see any face because he starts facing from 60 mm. Do you remember? Because for him, this part of the raw material doesn't exist. Do you remember? Because for him, this part of the raw material doesn't exist. In fact, you can see that the insert is inside the piece. In the program, we might be a bit less precise when getting close to the piece. Then what does he do? He moves away and then gets closer to the piece. Where does he get close? Here it is, right here. He approaches as if the cylinder didn't exist, because for him, the cylinder doesn't exist at this moment. You see, and so on. Control program, let's remove the single block and start again in 3D. Do you see? Defining raw material is crucial. It's an incredible programming power. It's not to be underestimated, so being able to define the raw material means having the ability to manage the castings as well. In my professional life, I haven't had this tool available, and I have to say that I'm sorry about that. I'm sorry because it's a very useful tool. Let's go ahead and do it. Our nice groove, so let's go back to edit. We go to turning, grooving, interruption, not cutting, but groove. Here it is, our groove. As you can see, it looks like this. Let's give it some data. So, I already like the selected tool. I like the parameters. So x0, z0. Now look here. You see, we use the data we have in the program. It measures this angle for me, and I'm going to take this angle. So we have an x of, here it is, 60, a z of minus 67, and a width. So I already like the selected tool. I like the parameters. So x0, z0. Now look here. You see, we use the data we have in the program. He measures this angle for me, and I'm going to take this angle. So we have an x of, here it is, exactly 60, a z of precisely minus 67, and a width approximately precisely. Since we don't have it, we'll delete it. A depth of 4 millimeters, an alpha 1, of an alpha 2, of, B1 and B2. We have the depth, which is 4.2. I apologize. So let's go to modify the header to 4.2. We said that here we have 15 degrees and we have all the radii at 1 millimeter. So 1, the D. I don't want to work in plunge. Roughing plus finishing, roughing excess material, and 1. So the D, which is the displacement of the grooves, is removed. Let's accept and simulate. In the meantime, let's go to Control. Program, let's set it to 100%. And as you can clearly see, the groove is absolutely perfectly done. Now let us start working with some of our powered tools. So, let us go back to our milling program once again. I really want to mill a very nice pocket. Here it is, a nice square pocket. Select tool, check cutters. Diameter 20 is too big, 3 is small. Need diameter 8, 20, a bit excessive. Here it is, let's use this cutter. Diameter 3, a bit small. So we need to do, however, radius 4, so diameter 8. Let's take an 8 cutter. That's perfect because this is a diameter. So, okay. We'll work at 2000 RPM, 50 millimeter per minute. Let's take a moment to rough it out, considering all aspects and details. For now, we'll proceed by roughing it out thoroughly and executing it in one continuous effort, just as we typically do in our usual approach. This method ensures that we cover everything comprehensively and efficiently, leaving no stone unturned. x0, 0, z0, which are the coordinates of center V, right. The width, which is 23 minato, is a square pocket, so it's also 23 m in length, with a radius of 4 meters. Here it is. You see, it's very easy. It's not tilted at all. It has a depth. Let's see. I can't quite understand the measurement. Let's not spend too much time on it. Ah, here it is, T3 of 3 meters. Perfect. How much do we want to remove in width with the end mill for each pass? It's an 8 millimeter end mill. We're removing 4 millimeter. Depth 1.5, so we'll do it in 2 passes. And I don't want any excess material. Let's accept and simulate. Identical number for cutting edge is impossible, not entered. I forgot a code. Okay. Okay. Probably. What I forgot could be in the tool table. Let's take a look. Tool selection, end mill, tool list, end mill 18. And as you can see, the number of cutting edges, I assume, you see, the number of teeth is 0. The machine can't calculate the feed rate. For the cutting edge, let's do a Z4. We click OK, it transfers to the program, we accept, and simulate. You see, every mistake, every knot comes to the surface. I was forgetting the thread. M48X 1.5. I mean, seriously, can someone please explain to me why that's not cool, right? Is this considered acceptable or appropriate? Now, I expected it to show it graphically, and now it does. We have 4 holes to make. They are 4 holes of 5 mm, 10 mm deep. Let's go ahead and do them, and then we'll take care of what we see. And if there's anything to fix, we'll fix it. It's time to make the 4 holes in front of our pocket, so drilling. Pocket. So, drilling. 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 Boring. And let us begin by carefully teaching. We slowly insert the drill bit. Here it is. 5 OK. And we've inserted it. Then we set an F of 0.06. It's an S and a V of 140 meters, like this. Z1 10 mm, pause 0.6, then OK. We stop at the bottom of the hill for approximately 0.6 of a second, a brief moment of a second or so, and then we give it the OK. At this point, what we're interested in are the positions for our holes. Here we give them the specific positions, such as at this point, we can assign the positions in several ways. For example, we can give it through X and Y, so real and effective positional coordinates with additional details. Or we can go back and say, hey, look, make me 4 nice centered holes. Look here. So A is the starting angle of the figure. 90 is the angle. The distance between one hole and another is 16. 32 is where our holes will rest. And there are 4 holes. We accept it, and by simulating, we'll have our holes. The only thing we need to do now is make sure that our holes are correctly tilted relative to the square figure. We accept it, and by simulating, we'll have our holes. The only thing we need to do now is make sure that our holes are correctly tilted relative to the square figure. The milling is centered on the piece. The only thing we need to do now is make sure that our holes are correctly tilted relative to the square figure. Milling in the center on the piece. If something didn't go right, let's modify the alphas. Instead, as you can see, having set the alphas to 0, the figures are in place. The thread, we've already done it in another tutorial, but since it's not difficult, let's add it. So we go back to Edit, and we go to Turning. Thread. Look at trading 1 and 5, M48 for 1 and 5. Perfect. We definitely need to work without a table because I don't think the past 48 is normally 1 and 5, so the step is good. Everything's good, linear and consistent, thread. Let's start by carefully giving it mainly our machining points. So, 48, length. In this case, we have to estimate a bit. Otherwise, we could go read the program because you see that it doesn't show it here. So we set it to -25 and then we'll see if we need to extend it. And this helps us a lot. Sorry, this is the initial Z. And this is the length, Z25. Safety distance, exit distance, thread depth, attack angle, increment. Excess material for the finishing pass. We accept it, and we're good to go. Good. I really wanted to make this video because the moment I realized that it could be programmed, I printed it. I said I have to make this video right away because it's really good, a good thing for those who have to do a lot of programming. Absolutely, this opportunity that ShopTurn offers is definitely worth considering. It's very valid and very easy. You see that we have the piece absolutely perfectly simulated, and we have an intuitiveness of the thing that truly, incredibly, and undoubtedly really leaves you amazed in every single way that you can imagine. ISO programming really becomes less necessary with this powerful tool. I hope I've shown you something interesting for your professions. For those who need to learn, especially I imagine that more experienced turners don't need me. If you liked the video, as always, a like, a subscription, a share. Let's try to get ourselves known. Thank you all for being with me, and see you next time. Good evening, everyone.